concentrate on the design of a cantilever retaining wall. Now we have the various parts of the retaining wall. Stem is the vertical part of the structure. This is the stem, so we call it one. So the stem cantilevers from the base, and we have the base, two parts of the base. We have the toe and we have the heels. Of course, if you look at the board carefully, you discover that the heel is the area where we have the earth backfield that is expected to be retained. All right, so this is where we have the earth materials to be retained. Now, on this other side of the retaining wall, we call it the front face. Why the side that is acting as the side to retain the earth is called the back face. On below the base of the cantilever, we could introduce what we call shear key at one end of the base of the cantilever retaining wall. We could introduce the shear key. Now, the essence of the shear key is to reduce the sliding of the retaining wall. And you could decide as an engineer to vary the position of the shear key. The shear key could be taken to be at the active zone, like we have seen in the diagram at the middle of the board. Or alternatively, you could decide to place the shear key just below the stem, okay? So all these are various alternatives which the engineer can choose from in the design of a cantilever retaining wall. The purpose of the design is to ensure stability of the structure. Of course, the failure can be failure due to overturning of the structure, which we call rotational moment, or the failure can be as a result of sliding of the structure away from its original position. Or we can have failure which is due to bearing capacity problem like settlement and shear when the structure is underlain on a very weak soil. All these are the various failures which can be encountered by a retaining wall. All right, so in carrying out the design, we must choose a dimension for each of these parts of the retaining wall that satisfy stability requirement of the slab. All right, so we can look at the overturning or rotational moment of the retaining wall in figure 1. Also in figure 2, we can see the sliding action of the retaining wall. Now, looking at the retaining wall, you can also look at a typical dimension of a retaining wall where we have the base, the footing base B, we have the depth D of the footing, we have the toe area, while we have the depth, we have the stem between 0.2 meter to 0.3 meter, the top and the bottom. Then we have the slantness to be 1:48, okay? All right, so we have the toe, we have the heel. You can look at D value. The D value is H over 12, while B is between 0.4H to 0.7H. So you can choose values between that range. Your depth of footing, which is your base, can be your height divided by 12. You can pick value from there. So once you can choose value from these values on the board, you can be sure of having a section that will satisfy stability requirement of your retaining wall. So we can pick section, depends on the height. We can as well ensure that the selected base, the base reactive forces that will be acting on the foundation is within middle of 1/3, so that we won't have too much stress on the toe. A situation whereby the stress, a section is choosing that will induce more stress on the toe, should be avoided as much as we can. So we must ensure that our base reactive pressure lies within middle of 1/3. Okay, so that is that for the base. All right, so we're going to look at the sliding of the retaining wall. Now, in calculating the sliding of the retaining wall, we are going to look at some of the parameters that are needed in the analysis of the sliding action of the retaining wall. Like we know that the retaining wall is having an inclined backfill. We have the inclined backfill at this point. Now we know the lateral active pressure is going to be acting also at an inclined angle. We have, let's call the lateral acting pressure to be this, PA, acting at an inclined angle to the wall. Next, we are going to look at some of the parameters. For example, the soil, the backfill soil, which is this soil within this zone, within the whole of this zone, we have the backfill soil. Now, this soil can have different properties. For example, the internal angle of friction of this soil can differ at various strata of the soil. But in this case of, for the purpose of the analysis of sliding, we're going to assume that the backfill soil, which is this soil, is having a uniform property in terms of internal angle of friction, phi, uh, and also the base soil. Let's look at the base soil also. The base soil, let's assume the same property, internal angle of friction for the base soil is the same. We have the cohesive stress of the base soil. Let's call it CB. Okay. Now let's look at some of the parameters. Remember that for this retaining wall to slide, it needs to move against frictional force at the bottom base, which is this point. So for it to move against friction at the bottom base, there must be some frictional resistance at the base. Now let's look at some parameters before we go into the formula. First of all, we know that coefficient of frictional force mu is a ratio of the static or dynamic frictional force to the normal reaction of the body. Of course, in this case, the normal reaction of the body, which is this retaining wall, comprises of the total vertical load on the retaining wall. Now, the total vertical load on the retaining wall, let's call it RV, the resultant vertical load. Now, we have the frictional force to be coefficient of frictional force times the resultant vertical forces. All right. Now, let's look at the angle of friction. Of course, we know that at the base of the retaining wall, there's going to be friction. And this friction is dependent on the nature, the cohesive nature of the soil under the base of the footing. So that means that the cohesion of the soil at the base is a factor that will determine the amount of frictional resistance that can be produced when a stress or a force is applied at the active zone. Remember, this is the active zone where we have the backfill. All right. Now, the angle of friction between the concrete retaining wall base and the soil underneath, let's call it phi b, which is the angle of friction or frictional angle, if you want to call it. Now, the internal angle of friction of the soil, we'll call it phi, which is the backfill soil. Now, there's a relationship between the internal angle of friction and the frictional angle at the base. Let's say that the formula is that the internal angle of friction or the frictional angle phi b at the base is equal to 2/3 of the internal angle of friction of the backfill, or you can say is equal to the internal angle of friction. So within this range, you can pick the frictional angle between this range. All right. Now let's look at the base. At the base, we said the cohesion of the base soil. Let's call it CB, cohesion of the base soil. All right. Now, in analyzing the retaining wall, like you see from the board, we are neglecting the effect of surcharge. All right. So, based on the slanting nature of the backfill, they are likely not to be surcharge load on the side of the wall. And if there's no surcharge load on the side of the wall, the pressure diagram becomes a triangular pressure. All right. Remember that for an active, the active zone, the active pressure is has a general formula. We have that formula to be gamma A equal to Y K A Z plus surcharge load plus Ka minus 2C root Ka. Okay, so this is a general formula for the stress at the active zone. Of course, in this case where we have zero surcharge, the whole of this entity becomes zero. And we are looking at a cohesionless soil, cohesionless backfill soil. So it means that C here is zero. So we are having the pressure at the base at this point. Let's call it the active pressure YKA. Of course, we know what our K stands for. Our K we know is 1 minus sine phi over 1 plus sine phi, where phi is the internal angle of friction of our backfill soil. Okay. Now we have this formula. Now this is the stress that is going to act here. Similarly, a similar stress is going to act here of this same value in this case, where our Z becomes zero at this point. We have the pressure here zero. When our Z becomes H, we have it to be Y KAH, gamma KAH, as the stress that is acting, the maximum stress at this point. Okay, so next we are going to look at the forces that are participating. Now let's talk about the forces that are participating. Now we'll start with the passive force. The passive force, of course, we know that the stress at the passive zone, let's call it the passive stress, becomes gamma. The stress at the passive zone becomes gamma kph. All right, that is the maximum stress at the passive zone. So in this case, we have this stress here. So if we want to analyze the forces that are going to cause sliding, we are going to look at it one after the other. So now let's look at the forces that are going to participate in this retaining wall. First of all, we know that the passive pressure PP is at this point. Of course, for the structure to remain in a state of equilibrium, what it means is that all resistive frictional force must be equal to the applied force causing friction. Okay, all right, the force causing it to slide. All right, so all the forces that are going to cause the structure to slide must be equal to the resistive frictional force. Now, in the resistive frictional forces, remember, this is the passive pressure on this zone. We're going to convert it to forces. So if we convert this pressure, which we know is our YKP, remember that Kp is an inverse of our Ka. All right. So we know that our Ka, like I said before, is 1 minus sine phi over 1 plus sine phi. All right. So this is our Ka. So the inverse of our Ka is our Kp, which is the coefficient of passive pressure. All right. Now, having done this, the next we are going to look at the forces that are going to act. Of course, this is the passive force. Remember, in looking at the forces that are going to act, what are the resistive frictional forces? The passive pressure at this end is going to resist the sliding effect of the retaining wall due to active pressure on this right hand side. So while this one is resisting it, this becomes our PP, which is part of the resistive force. Remember that this is a pressure, so if we convert our PP, which is a pressure that we know is this, we can convert it to become a force. If it becomes a force, it becomes the area of this shape, which is a triangle, times the area of the shape becomes the force, which is half times h times y k p h. All right, so if we do that, we have 1 over 2 gamma, sorry, I call it y, gamma k p h squared. All right, So if we do that, we'll convert this to become a force instead of pressure that it is. In a similar way, this one becomes a force here. We can multiply the area to have it as 1 gamma Ka capital H on this side. All right. So let's take the total forces. Let's call the total force due to the pressure on this side. Let's call our passive force PP plus the force due to the cohesion of the base. Remember, the cohesion is a pressure, so we'll convert it to become a force by multiplying it by the distance, the soil, the distance under the base of the footing. So it becomes CB, which is the cohesion of the base soil, times the breadth of the footing. That will give us the force, the frictional resistive force due to cohesion of this base soil, plus the coefficient, the frictional force as a result of the vertical, the loads that are acting on the footing. Remember, that frictional force, we have that force to be mu, which is this, mu times the resultant vertical load. And of course, we know that mu is equal to tan phi b, where phi b is the frictional angle of the frictional angle between the base of the footing and the soil under the base. All right. So we are going to look at that. So if we do that, it becomes tan phi b, and it's equal to the total resistive frictional force. Now, having gotten the total resistive frictional force, now the total force that is causing the sliding is equal to the active force, the active pressure, which we can convert to force. We convert the active force, we know that it becomes a PA cos alpha B, where alpha B becomes the angle of inclination of the back field. So if we do that, we have PA cos alpha B. All right. Now, if we look at that, we also know, if we resolve that, we have this. We also know that our ROV, which is the resultant vertical force, uh, we are also going to resolve a component of this force, resolve the vertical component, which is going to act as a vertical force on the heels of this footing at this zone. So we're going to resolve this, which will give us a PA sine alpha B. That is a vertical component. And apart from that, the self weight of the soil on this place is also going to act on the heel of the retaining wall, just as the self weight of the soil on the toe of the retaining wall is going to act as part of the vertical forces that that makes up our ROV. So our ROV is going to comprise of both the self weight of the soil, the vertical component of the active pressure, and the self weight of the soil at the passive zone. Okay, so this is what we have for that. So we can say that the total frictional resistive force, which is this, is equal to the total force causing sliding, which is PA cos alpha B. All right. Now, if we do that mathematically, we can say that the total force, resistive frictional force divided by the total force causing sliding is equal to 1. All right. So that 1, that is under equilibrium. If we say it's equal to 1, that means we are looking at it under a state of equilibrium. All right. So under equilibrium, they are supposed to be equal, but we are not going to base our safety on equilibrium. We need a situation whereby we can guarantee safety by increasing that 1 to be by 60% to make it 1.6. Okay, so we can take it to be 1.6. Some people can decide to make it up to 2, which is about 100% increment of the factor of safety against sliding. All right, so this is what we have as the factor of safety against sliding. So what we are saying is that the minimum factor of safety against sliding, let's say, it should be taken to be 1.6, or it could be 2. So it's either is greater than 1.6, or you can take it greater than 2, whichever one that deems suitable, economical. But
1.6, I think, is economical for your design. All right. Now, also take note that our PP, we know it, the PP, which is a force, we've converted it to force. Our active pressure here also, which is this, if we multiply the area of this shape, it becomes 1 over 2 times gamma KAH squared. That becomes a force also. So, but we're not going to do that since we are just trying to obtain the expression for the factor of safety against sliding. All right, so this is bring us to the end of the lecture, talking about the factor of safety against sliding. Alternatively, in a case where we have the backfill that is not inclined, we can, and we are going to have a surcharge pressure. So if we have a surcharge pressure, the surcharge pressure is a uniform pressure that is acting laterally. So we can have that surcharge pressure acting on the cantilever wall in this direction. And we also have the surcharge load, which is a uniform load. Let's call it Q, expressed in kilonewton per meter square. So in this case, where you have a horizontal backfill, what happens is the surcharge develop a lateral stress on this direction, which is going to be multiplied by the coefficient of active pressure. All right. So when you do that, you are going to also discover that the surcharge load also acts as part of the vertical load, which is our RV, on the heels of the retaining wall. Okay, so that is just the difference in terms of the sliding action of the retaining wall in determining the sliding action. All right. So I believe with this we can be able to solve a problem on sliding of the retaining wall. Once the section has been chosen, we can carry out investigation to ensure that our chosen section meets up the minimum factor of safety against sliding. All right. So thank you very much for watching. If you find this lecture interesting, do well to hit the subscribe button. I remain your host, Engineer Baga. I'll see you in our next class. Stay cool and have a wonderful time.